Hi, I'm Jon McLoone. I lead the technical services team for Wolfram Research in Europe, and my talk is going to be about non-invasive cancer diagnosis using cameras that you swallow and image processing on the results that they capture. Hello everybody, I'm Jon McLoone. I have a range of things I'm involved in at Wolfram Research, but one of my key roles is that I lead the technical services team in Europe. So we have a group there that does consulting projects using the Wolfram technology for different outside customers to tailor it to do what they want. Most of that stuff's encumbered by non-disclosure agreements that we sign, but this particular one is publicly funded, so I can talk about it. And so this is a project that we're involved in. We're at early stages on, but we've already got a couple of bits and pieces I can show you. But we're working over the next year or two to try and improve the diagnostics of colon cancer. So it's a fairly mild warning on here, but I do have a couple of pictures, but I've kept all of the horrible, gnarly pictures away. Let's set the scene first of all, which is that, as you would imagine, being called bowel cancer, it's kind of a significant thing. It accounts for, at least on the UK rates, 26 deaths per 100,000 people a year. So that scales up pretty fast. In the UK, 16,000 people a year die from bowel cancer. In the US, that's 51,000. So it's a pretty significant cause of death. And annoyingly, it's highly treatable, that if it's detected early, it's very treatable and quite survivable. But of course, you can't see what's going on deep inside you, so it tends to be that it only gets diagnosed quite late, and that results in deaths. Now, there are some early signs that trigger people to look more closely, but in the end, the only diagnostic that is fairly definitive is colonoscopy. So there is this long camera that is on a tube, and it has a camera, it has some lighting, it has some control system up it so you can pilot the thing, and you have to stick it deep inside you to have a look around. And it feeds back real-time pictures to the person driving the thing as they navigate around your bowel to have a look at what's there. Now, there's a bunch of problems with that. One, obviously, is patient aversion. People really don't like the idea of that, which, of course, puts people off having early diagnostics, and that makes the outcomes worse. It's also got a real skill problem that you've got somebody who's got to both pilot and diagnose, so and they have to be there to do that. So it's got quite a demand on the operator in order to do this. You can't just get some random nurse to go and check you out. It actually takes some skill. It requires hospital facilities, so that's expensive. You've got support staff, you've got rooms, and it's actually not without risk. So the current rate apparently is 0.5%, 7% perforation. So you might be completely healthy, and after you come out from this, you've got a hole in your stomach because the operator drove it badly and poked it through the side of the bowel wall. So the rate's not high. These guys are reasonably skilled, but it's still significant. And so you might end up with a hospital stay even if there was nothing to diagnose. So here's the kind of the fresh idea that this project that we're involved in with a whole consortium of different partners is to try and push forward the idea of the capsule endoscopy. So there is this pill, and I guess you can guess from the size there, I'm not quite sure what the exact size is. It contains a fully self-contained camera, light, and power system. And I believe even kind of Wi-Fi is built into this thing, and it makes a fairly large pill, but quite swallowable. So it's patient-friendly. All you have to be able to do is swallow a pill. You have to retrieve it afterwards, but you can do this in your own home, in the privacy of your own home, in the comfort of your own home. There's no operator. You are the operator. You just swallow the thing, sit around for a while. You're given some preparation to help speed its journey. Trying to find the right euphemism. But it's essentially risk-free, but it still has a problem, which is that now instead of a few minutes of real-time footage, it comes out with thousands of photographs. It's taking multiple frames a second at its highest rate. I think it's got some detector of whether it's moving, so it doesn't waste too many frames, but it comes out with thousands of frames which need reviewing. And that review is still at this point a skilled process. And in a way, it's worse now because you've got these thousands of images, whereas before, when you were controlling the thing, if everything looks good, you kind of just send it in further and look somewhere else. So ultimately, of course, what we want is to move towards fully automated diagnostics. The promise here is that machine learning could just take this video and give you the all clear. And, it might run for a few minutes as it runs through the thousands of frames, scores them all, and then tells you what the outcome is. And of course, if you follow that through, that's an immediate reduction in cost because you don't need the skilled operator. But it also it has a knock-on effect then that it can scale much higher. So first of all, you're scaling to more images. We can actually get the entire digestive tract. So you're not limited to those places that you've looked. You can look everywhere, literally. But also the promise here is that if in fact this was cheap enough, we could use that diagnostic much more readily. So rather than waiting until there are some very bad warning signs and deciding that maybe a colonoscopy to check whether it's bowel cancer is needed, it could potentially even be done as some kind of routine middle-age screening. You've hit the age of 50, it's time you swallow the pill, and then we'll give you the all clear for another decade or whatever. And if we can catch, as I said, because it's one of these cancers with early detection has good outcomes, getting it before it's progressed actually could reduce a lot of those deaths. So that's the ultimate aim. But we're far from that at this point. So, as with all machine learning tasks, pretty much, the Achilles heel is data. We've got the devices now, but we don't really have the training data. So the project we're involved in is about trying to deal with some of the practicalities of how does one run these things at scale, and to try and improve the process of reviewing footage, and to build training sets, and then use those to do automated machine learning to then try and assist the diagnostics. So there's a whole bunch of stages to that. The aspirational goal is a fully automated diagnosis. As I said, you swallow the camera, you hand it in, an hour later you get an email saying everything's fine. Stage one, we're focusing on a review interface that allows us to tag the images. So a skilled operator will still need to look at everything. We're trying to figure out some ways to make it more convenient to look at. But the idea is here that they're going to tag this looks like cancer, this doesn't look like cancer, and build that training set, so that we can then go to a stage two where essentially the same kind of interface will be in operation, but instead of saying, look at frame 1, look at frame 2, look at frame 3, it'll now say, here's the frames that look worst. And you'll be able to say, show me the most dangerous looking images first, and you'll be able to mark those up. Show me everything that's above a 10% risk of looking like cancer. Maybe look at a few of the ones that are marked as clean to make sure they're good, but some prioritization. So we build this virtuous feedback loop of the act of trying to use it for diagnostics improves the training sets to improve the diagnostics and ultimately step towards this long-term goal. So let me show you the first prototype tool that we have. The video has already been uploaded. We're not doing any kind of automated database connection yet, so it's file-based at this point. And the idea is here, and let's do this straight away, I'll do open new, and we'll pick a video file that's been captured. And this is doing some work now. You can't see it, but we've got an asynchronous process going on here, going through that video, doing some preparation work to set it up for this next stage of the interface where we review the content. So it's going to have a look here at where we've got so far. And you can see it's processed 431 of the frames out of the 8,600, but it's still working in the background while we're in this review step. And the basic idea is I can go over the thumbnails here and have a closer look. So here's, we're looking down the length of the bowel, we're sort of facing forwards. This particular image has a big bubble in the way, but you can see the areas. So this is an obstructive bubble that's going on here. That's the direction of travel, and then this is bowel wall we're seeing around the outside. And this review interface then allows me to click on this image and say, well, that one looks unclean, or maybe I'm unsure, or it's clean, or I can select all of those and say they all look good to me. Oops, sorry, all look unclean to me, let's say, and go on to the next page and continue to review, and so on. So it's a simple, basic thing of pulling out the frames, setting them up so that there's a fairly quick process to marking them. And then we've got an export where I can write those files out to, let's say, my desktop here. And if we go across, this folder's now just appeared. And we've got a data file here. Let's open it in Mathematica. So here is the data file that shows the human classifications that these things were marked as cancer, and I didn't have any that I marked as not cancer. This is dummy information at the moment for the machine learning classification that when we get the first classifier back from the team working on the machine learning, this will start putting in its opinion, and this is then all set up ready for post-analysis, along with folders of the images that have been marked that match up to the IDs within the data file. So let's talk for a moment about how the toolset helps. I picked out what I thought were the kind of key elements of Wolfram language that's helping us here. So the first step is we have a whole bunch of process control. We're using FFmpeg for the video to image processing because Mathematica doesn't currently support MPEG video. I'm very pleased to hear the work of, I presume, Marcus, you're involved in this, are you? Shadi's work on adding video functionality, because we plan to completely scrap this once 12.1 gives us native handling of video. But at the moment, what we're doing is we're using start process to start an asynchronous process of FFmpeg, taking the video and slicing it up into frames and writing them into a folder where we can pick them up as JPEGs. And process status is allowing us to watch how that's doing. Now, the tool as I have it there is doing no real image processing. It's just putting the images up on screen. But so there's a line I always tell people when I talk to people about machine learning for the first time. I always tell them that machine learning is good when you are data rich and understanding poor. And that sort of classical methods are better when you are understanding rich and data poor. So while we're very low on data, there is a belief that the things that we can detect through human intelligence and remove from the image should be done to allow the machine learning to be able to focus only on the bits that we don't understand, which is what does cancer look like. So we do have some image processing that we've been doing to detect and remove the obstructions, which at least at the moment appear to be very consistently recognizable. So for example, the bubbles that we saw in that earlier image seem to be about the only thing going on down a relatively clean stomach that have very high kind of edge entropy. And so we've used that kind of characteristic to be able to pick out the area that looks like bubbles and take an image and debubble it. So we can mask out those areas that we think are obscuring anything that's worth seeing. And we get the same thing with unclean, where there is sort of blockages that we're finding that color seems to be a pretty good indicator that the bowel wall is generally fairly pink, and that things that get in the way from you seeing it generally are not fairly pink. So with a little bit of contrast and color detection, we're able to pick out some of those obstructions. So this is some of the auto filtering to try and take the image and mask away the bits that aren't actually any use for detection, because we're not actually seeing bowel wall. And they have varying success, sometimes a little bit over-conservative at the moment. But the idea is that we're going to try having this pre-filtering so that machine learning is only ever looking at bowel.
Actually, do you have any images of cancerous things?
I don't actually have any with me, and I thought on the basis of I didn't need to show anything unnecessarily grim, I would just show the bare minimum pictures. But basically they are, I believe they're sort of fairly small nodules that have a kind of a profile. So there's sort of a polyp that grows out of so they stick out a little bit, they have a bit of shape, but they also are colored a little bit differently.
So the obvious question is these debubbling and stuff don't
we don't know that at this point. So we're going to try and fine-tune these things. I mean, in the long run, with enough data, of course, the machine learning should learn that bubbles don't ever affect the outcome and will filter them out for itself. So this is thought as an intermediate thing, and we're playing around with that. But the pilot's gathering data hasn't really kicked off yet, so the machine learning team is just kind of waiting, and they're giving us these hypotheticals on this small set of data that we have to work from. At the moment, we're speeding things up with parallelization, so we have the usual parallel tools where we can get through many more of these processes in parallel. Talking to Shadi, it sounds like a lot of the video map type functionality, because we're not going through this loop of writing a JPEG to read the JPEG in, to do something to write a JPEG out. The pipeline of throughput might be fast enough that we can dispense with parallel. But we're leaving it in for the moment anyway, because the ultimate goal, of course, is some really scalable diagnostic system. So you want to have some big Amazon cluster potentially having thousands of patients uploaded to it. Parallelization to make sure you're not waiting weeks for the answer might still be important. So the jury's out on that part. Of course, the thing you were seeing, it's all just standard dynamics. So we've got event handlers and tooltips and buttons for the forward and back, and import and export being driven by buttons. And yeah, these all it's just a CDF like everything else that we do pretty much. And then there's a data processing element that you haven't really seen there, but as we go into production, the system we have to deal with has an elaborate patient record mechanism, and we need to be able to read that in, augment it with either the automatic supposed detections or the manual markups, and write the thing back into that system. That's all XML based, so we're going to be using things like XML element and export string to be able to take what you saw there as a bunch of associations and write them into the appropriate XML structure. And we're going to have to deal with a bunch of the OAuth type authentication or database integration tools to be able to read and write directly. At the moment, we're just being sent files backwards and forwards. So that's the project. I should wrap by giving credit where it's due. The consortium is quite large. So we're at the moment taking care of this user interface and image processing side, but not the machine learning. But there is a follow-on stage that we hope will get funded where, in fact, there is a separate machine learning problem for trying to figure out who will benefit. And I mean that both on a local level for the individual, that there may be characteristics about certain patients will benefit more from this than the traditional method, but it's not clear that that's true. But also on a macroscopic level, that which hospitals will benefit. If you've got really efficient colonoscopy teams, then the cost benefit might not be worth the switch. And what we want to do is to use the data sets on both sort of descriptive logic of things like costs and benefits, together with patient-level data to be able to start making predictions about the cost and the benefit trade-off for individual patients, and then on high level. The lead on this is Sjoerd Smit, who you might know from, he writes on the blog and community occasionally, particularly about Bayesian statistics, and he's done most of the work on this. I've been slightly more hands-off with design and sort of brainstorming, but the coding's all been Sjoerd's. We're working with Corporate Health International, who are dealing with the capsules. A whole bunch of NHS bodies, so Arden and Gem, Highland Health Board, and Highland Islands, Highland Health Board and NHS Arden and Gem are commissioning bodies of the National Health Service in the UK. Barcelona's university are providing the machine learning team, and then we're getting some extra kind of facilitation support and particularly money from the satellite catapults and the enterprise funding bodies within the UK. So the team's kind of quite big and sprawling, but we've got our little bit of it, which you've seen the first steps of here today. And that's all I had to share with you. Are there any questions?